Hello, everyone. Hello. Thank you for having me. It's a pleasure being here. I'm here to talk about Kaspa and why Web3 developers should care about Kaspa. Now, I think some of you would find this question a bit intriguing because Kaspa is a layer 1. We know that we don't already have smart contracts, so why should you care if you are in the Web3 world? The key takeaway here is that if you want to have a strong Web3, you need to have a strong layer 1 that the Web3 will work over. And what I hope to convince you today is that Kaspa is an exceptionally strong layer 1, maybe the strongest one yet. So in this talk, I'm going to talk about what Kaspa achieves and about the performance of Kaspa. And I'm not really going to talk about how Kaspa works. It's an entire different thing. But if you go into YouTube and search for GhostDog 101, you will find a short 2.5-hour workshop I give, which goes over what's going on under the hood for Kaspa. But in this talk, I'm not going to talk about the internals of the tech at all. So let's stop and think what we would like a layer 1 to have. What are the important properties? So first, it should be secure. This one goes without saying. It should be decentralized, because if it's not decentralized, why even use blockchain technology? And it should be performant, and this one actually is a complicated one. There are all sorts of performance you should care about, and I'm going to talk about all of them. It should be reactive, in the sense that if you want to do something, post a post on your decentralized Twitter or whatever, it should happen fast. You don't want to wait 10 minutes or 5 minutes or even 30 seconds. It should be environmental and sustainable. It should be something that the world can carry. It should be cheap to use, right? You don't want any post you make or any transaction to cost a lot of money. And you want even the layer 2s that you build over it not to have to pay a lot of utility. You want the validators, whether they are miners on the proof of work or the validators and block creators on the proof of stakes, you want them to be properly compensated for their work and their contribution to the network. And you want it to be adaptive, which is a tricky one. It's something that most people haven't even thought about, but it's actually very crucial, as we are going to see. And I'm going to explain this as I get to it. Okay, so what is Kaspa? On the screen behind me, what you're seeing is not like an illustration. This is a real recording of our testnet 11. Each one of these squares is a block that can carry up to 300 transactions. And this is the actual speed with which the network is performing. It could do I'll get into numbers very soon, but what I want you to notice is that it is indeed very, very fast. But it's not just the consensus protocol. Actually, it's a lot of interesting innovations all rolled into one project, and I'm going to state just some of them. But on the surface, first of all, it's a proof of work. It's based on what's called a DAG. If you know, then you know what it is. It's currently UTXO-based, but we are going to extend the model as we need. But what I really want to argue is that it satisfies each and every item on the each and every item on the desiderata I stated earlier. So let's just go over them one by one. Well, the security that Kaspa gives you is the same security as Bitcoin. The Nakamoto consensus security, which is better than the BFT security we'll get from proof of stake, which is, in a sense, the best security possible in a decentralized setting. And it's also more decentralized using proof of work because you have this extrinsic sorts of voting. You don't vote with the coin that is generated by voting, which resolves a lot of issues. It is decentralized. Okay, so one characteristic of Kaspa is that it is ASIC mined. And a lot of people think the conventional wisdom is that ASIC mining is decentralized. Well, I argue that the conventional wisdom is wrong. And the main key here is that having a very high VPS keeps the network decentralized. Because if you have 6,000 times more blocks than, say, Bitcoin, then you could carry 6,000 times more miners, which have the same time of return, sorry, they have the same revenue return time. So if Bitcoin can have about 120 miners or pools with a return of investment of about a week, then in Kaspa we can have 1.5 million of them. And one strong indicator of this is that even though there are very huge monstrosities of mining machines, the best-selling ASIC is still the smallest one. It is cold, it is cheap, it is energy efficient, and that's why you see that we have many, many, many small miners, even though large miners are available. Its performance, so the first thing is that it has a lot of throughput. Now, the conventional wisdom says that proof of work can't be performant in the sense of throughput. We see it in Bitcoin, we see it in most of the proof of works. But again, the conventional wisdom is wrong. If you go and look, you see, as in the animation before, that the ghost DAG ordering rule actually allows you to remain secure while producing a lot of blocks, keeping the security benefits of proof of work while giving you a lot of throughput. So on the testnet, we have right now 10 blocks per second, which translates to 3,000 transactions per second. And we see that the nodes can carry queues of up to 600,000 pending transactions without having any significant slowdown. And all of this is just on the layer 1. I mean, you could use Lightning or Polkadot or any layer 2 that you like. You can import it to Kaspa, and you have a lot of bandwidth to implement this over. Okay, the next conventional wisdom is that high throughput requires strong computational abilities. And also here, the conventional wisdom is wrong, because ghost DAG can be implemented very efficiently. In fact, all of the performance I told you about in the testnet with the high TPS and high block rate and everything, nodes are running this network efficiently on computers that cost as much as $100. You don't need the extremely expensive validators like you need in a proof of stake. The next wrong conventional wisdom is that if you have high throughput, then you're going to need a lot of storage. This is also wrong. Because we use proof of work and not proof of stake, this gives us the ability to use unique solutions for pruning data, for removing old data securely. And we use a protocol invented by Michael Sutton and myself for pruning data securely, and the mining with logarithmic space adapted to DAGs to prune the headers securely. And recently we had a breakthrough which actually applies to all of crypto and not just to UTXO and not just to Kaspa, that allows us to significantly and easily counter state bloat without resorting to stuff like accumulators and statelessness or demurrage or that kind of stuff, just this kind of magic formula that allows us to limit how much the state can bloat. And if you want to read more about it, you should look up for the Kaspa Improvement Proposal 9. It was purchased about 2 weeks ago, and I think it's a real game changer. Okay, reactiveness is essentially how long you have to wait since you push the button and until the network agrees on whatever you did. And the conventional wisdom says that in proof of work, you don't have good reaction time, that proof of work networks are slow to react. Conventional wisdom is wrong. The ghost DAG protocol provides instant confirmation. Now, when I say instant, I mean as fast as the internet, because you can never be faster than that. But it's a proof of work where the limit on how fast you can confirm transaction is completely dominated by the network conditions and not by the security of the protocol. So essentially, it's as fast as proof of stake. And one application for this is that you could do rapid settlements. If you do side chains, you can settle them on the main chain, and you can do this as fast as you can do it on proof of stake, even though it is proof of work, so you don't lose speed. The conventional wisdom says that proof of work is very, very energy intensive. And here again, the conventional wisdom is wrong. Because there are ways, essentially by using a very, very ASIC-friendly mining algorithm, we are able to make almost all of the expenditure capital expense and reduce the amount of operational expense and essentially the amount of electricity you need to burn for mining. And there are also future plans for using optical mining, which should make it even more capex heavy. Now, the chip is really straightforward. If you have a lot of transactions, then you would pay less for each transaction separately. This is really the most straightforward one. Now about validator compensation, or the so-called fee market problem, or the security budget problem. And again, we have this conventional wisdom which says that in proof of work, the fee market doesn't kick in, doesn't start to work before the network is fully congested. And again, the conventional wisdom is wrong. And this is a consequence of parallelism. Now, I'm not going to go into the math here, but essentially the fact that many blocks are created in parallel means that the fee market becomes active way, way before the network is at full capacity. And not only that, it avoids this weird bidding war dynamic you have in say, in Bitcoin, where if you are one Satoshi below, then you are definitely out with probability 1, and then you increase by 1 Satoshi, you're definitely in. And no, the parallelism smooths things out in a way that means that the amount of fee you pay reflects much better the quality of service you expect to get. Okay, so now I think the coolest aspect is the adaptiveness. So this conventional wisdom is so conventional that a lot of people don't even think to go around it, and there are actually impossibility results that in some models say that it's impossible to be reactive to network conditions. In all protocols that exist today, when you create the network, when you launch the network, you have some parameter, which is called the network delay, or a bound on the network delay, and you're saying stuff like, okay, maybe my network has a delay time of 1 second, but I'm going to set it to 10 seconds because I need a margin of error, and you will always need to have this margin of error, and you could never adapt. The only way to adapt is to do a hard fork and reparameterize the protocol. And it seems that the conventional wisdom is wrong here as well. There is this brilliant new protocol, not yet implemented, called DAGNITE, invented by Michael Sutton and Jonathan Sompolinsky. And DAGNITE has this incredible property that it is adaptive. It does not require a bound on latency, and this has far-reaching consequences. First is that you don't need a margin of error. You can always operate as fast as the network allows. And if the network improves, the protocol will automatically become faster in its confirmation times to accommodate the better network conditions. And if there is some sort of calamity that makes the network conditions deteriorate, then the protocol will automatically slow itself down to remain secure. And this will allow us to get better speed and better security, and essentially the best speed possible. If right now the best speed possible is by taking a bound on the network latency, which is almost always true but needs a margin of error, DAGNITE will allow you to remove this bound completely and work and be as fast as the network actually is, not as the best bound you can feel comfortable with. Now, we conjecture that this kind of property is impossible in proof of stake, and only proof of work is able to get it. And by consequence, this means that DAGNITE will always perform better than any proof of stake protocol you can ever come up with. And that's about it. I hope I convinced you that Kaspa has something unique to offer, and please come visit our booth. Thanks for having me.